Welcome everyone to the RISC-V Summit presentation, given today from Roman Shaposhnik, CHO and founder of ZEDEDA, and myself, Kathy Giori, also Ecosystem Engagement Lead at ZEDEDA. And a little bit more about us. Roman has been a hacker from an early age, Sun Microsystems, still hacks today, one of the top contributors to our open source project that we'll be talking to you about today. Was a wrestler, has all sorts of interesting interests well beyond tech. I can vouch for that, and is a craft brewer aficionado. I'm a little bit more on the user advocate side because I'm an electrical engineer, and so I like to break software more than produce it. And I've been involved in open source for a really long time, like to do things, but what really excites us about today and RISC-V and open source software is that we're looking to get the entire stack open source, from all the way from the silicon through the board designs, through the software. And so, being at this RISC-V Summit, we're not going to be talking about chip designs or board designs, but we do want to connect those designs all the way up through the software stack. So, you all probably know the history of RISC-V, but it's really been exciting that since about the 5th generation evolution, the Berkeley folks, David Patterson and grad students and now famous Sci-5 founders have really spearheaded getting RISC-V into industry. And there's a lot of universities and community efforts behind it as well. So even though it started mostly on the microcontroller side, we're now seeing that server class has been coming in the recent years. We're looking forward to seeing what new designs come out in 2022. I'm actually on BeagleBoard's board with, you all probably know Drew Fustini really well, and he's been spearheading those efforts. So having upstream Linux kernel development start early on in the chip design and development is super important and super just really handy for the rest of us who then take that forward and turn these designs into boards that industry can use. So, and then also, there's numerous customizations that you can make for the industry rather than have a one-size-fits-all type of chip. So I'm going to hand it off to Roman, who's going to describe what open source software we've been able to run on top of RISC-V. Take it, Roman.
Well, thank you so much, Katie, and thank you so much for such a wonderful introduction. Katie, by the way, is way too modest. She's actually very much involved in RISC-V Foundation, even from what I understand, and various projects around it. So ask away any questions that you want about RISC-V or foundation of Katie. I will be talking about the software more than the foundation or sort of the chip design itself, and I will try to sort of start with the good news and the bad news, right? The good news is all of this wonderful excitement that Katie talked about. Now, as always, on the software side, there's a bit of a bad news, right? Because, software is always a bad boy in the system design. Well, first of all, if you look at the software, any computer is only as good as the software ecosystem that it can support. And today, that software ecosystem is still sadly very much driven by x86 architecture, which means that pretty much everything that you would interact with would have been optimized for x86, and even ARM a lot of times is actually an afterthought, let alone RISC-V. Now, outside of x86 and ARM, you still have a few architectures that are still very much alive. Open Power and MIPS definitely come to mind, but those are sort of the long tail of software ecosystem. So if we're talking about the RISC-V, one of the first questions is how can we get the most of the software as quickly as possible, because after all, we need it, right away. And a lot of times people just say well, let's just port Unix, let's just start with some kind of a Linux distribution, it will be good enough. To me, let's just port Unix means let's just, do C. There's tons of other ecosystems nowadays that you should not forget: Java, Golang, Rust, Ruby, Python, Perl. All of that needs to be ported. That is just a given. Now, the good news in all of this bad news is that all of these ecosystems, are very rapidly coming to RISC-V, so that I'm actually not worried about. But what I'm worried about is that within the rest of the user space software, we sort of still seem to be stuck at this, what I call Linaro effect, which is let's just take all of the old school software and make it available for this architecture. And that in and of itself is not as bad an effort as it sounds. It just takes a way long time. So I don't think that a Linaro-like effort is an answer, because there's just like way too much stuff to port. But I very much do think that Android-like thing is very much an answer, because Android gave us a glimpse at how a non-traditional operating system can be designed in such a way that it completely lifted up ARM to a status that it enjoys today. Remember, it wasn't Unix that did it, it was actually Android. Now again, if you look more into how you would build such a specialized operating system, now again, you can do Android, and as many of you know, Android actually does exist on RISC-V nowadays. But you can also take a look at cloud native plus specialized operating systems. And cloud native means that, a couple of things, different people treat it differently, but to me, it's everything is a container. Your infrastructure is immutable. Container orchestration platforms basically manage your entire lifecycle. Now, there's a few examples of these specialized operating systems, CoreOS, Chrome OS, they're basically operating systems that all of the public cloud providers use. And then finally, there's EvoS, which is we are going to talk about today. What's interesting about EvoS is that it completely bypasses this whole question of operating system being a single integration point, and instead it embraces containers and virtual machines. So in a way, it offers us a way out of how to port the entire software ecosystem. And basically says like, well, we can just port what makes this operating system go, and then everything else will be done step by step through virtualization, which, by the way, actually may even include emulation, and then we can even run, some of the x86 or ARM software on RISC-V. What is EvoS? So let's talk a little bit about that. EvoS wants to be to the edge what Android has become to mobile, so that's our aspirational theme. But more practically speaking, what does it actually mean to be on the edge? Well, it means all of those things that you can see on this slide. It can be a computer that's bolted to a vehicle. It can be a computer that's, at the factory floor or at a windmill. The interesting bit about those computers is that they're definitely not IoT, because we're talking at least, 2 to 16 gigabytes of RAM, a few decent, typically x86, sometimes ARM, but hopefully, very soon RISC-V cores. So these are definitely not IoT boxes, but they're also not server like grade, computers, right? So it's this very interesting kind of spectrum of how edge means different things to different people. Now, again, if you're still confused about the edge, I highly recommend downloading a white paper that we have done at Linux Foundation Edge. It's called Edge Taxonomy White Paper, and it basically talks about different types of the edges. EveOS is focused on the two. In that taxonomy, they are called smart device edge and on-prem data center edge. And these are basically the computers I was showing you, right? Bigger boxes than IoT, sometimes, smaller boxes than rackable servers, definitely very network oriented, definitely very security sensitive. If you look into EvoS and how it tries to embrace, RISC-V, EvoS itself is very much focused on virtualization, like I said, which, by the way, is a very much emerging area in RISC-V design still. We're trying to start participating in making that particular enhancement to the RISC-V specification a reality. But obviously, sadly, there's still not really much of a silicon with those extensions available. So we still have to run more on the, in the virtualized environment ourselves. But EvoS actually has a mode of running just purely on bare metal without, virtualization. So, that is also available to us. Now, on top of that virtualization, we effectively have a few things that we do. So first of all, we do storage management, which is very similar to how Chrome OS does it. So in order to update EvoS itself, we do partition A, partition B. So again, it is very much an immutable infrastructure. And EvoS itself only takes 250 megabytes, which means that because of dual partitioning, you still waste about 500 megabytes on EvoS, but it's pretty decent even by the embedded operating system standards. On top of that, we basically take away one single core, and we take away about half a gigabyte of memory. And in all of that space, we're running essentially a whole bunch of Eve daemons, all, by the way, done as microservices themselves, all container-based, running all on top of the container D. And those daemons effectively provide services to the rest of the system. In that sense, EvoS takes a lot of inspiration from cubes. We even have a mode in which all those daemons can actually be put into individual virtual machines. But it's that, defense in depth, security first design that sort of separates EvoS from a lot of the attempts to just take an existing operating system like Ubuntu or CentOS and bolt it onto the edge. One of the daemons that we run is talking to the Eve controller, and Eve controller is something that actually tells the system what to do. So once everything is said and done, the system can basically do your typical cloud native operations, like start a VM, stop a VM, start a container, stop a container, create a bit of storage, remove a bit of storage, create some kind of a network, remove that type of network. What's interesting is that because we're, again, so focused on virtualization, we can actually trick VMs and containers that run inside of those VMs into thinking that they're running in an environment that is not what the computer itself exists in. So for example, we can basically trick a virtual machine or even a container into thinking that it is part of the, let's say, Amazon VPC, right? Virtual private cloud, which means that we're effectively doing all of the plumbing for IPsec and establishing the VPN connections back to Amazon behind the scenes. And all that VM knows is that it just sends traffic or virtualized NIC, and that traffic just ends up where it needs to go. So again, EvoS tries to keep VMs and containers as dumb as possible by essentially providing all of these common services in what we do on the other side of the hypervisor. So what really excites me about Eve these days, though, is, of course, we do a lot of that on x86. Like I said, a lot of our customers are still x86 based. We support ARM, so ARM is very much a first-class citizen. You can take a Raspberry Pi and run EvoS on top of it. But even with Raspberry Pi, it feels to me that we're still missing a fundamental openness in the entire stack. And to me, RISC-V might actually be this final piece of the puzzle that unlocks the entire open source stack on, down from the silicon all the way up to the application to be completely open and free for anyone to use and innovate. And that would be amazing. And in fact, if I were to take a guess at what could be a killer app for the RISC-V ecosystem, edge computing might just be that. So how does EvoS blur the line between cloud and the edge? Well, in order to discuss that, let's actually talk a little bit about the ecosystem. So I'll hand it over back to Casey.
Thanks, Roman. That was a really great intro to EvoS. And like I say, I'm just inspired as you as having the full innovation all the way to this core common infrastructure. And although for me, embedded Linux was always the standalone thing, what I've learned in this environment that ZEDEDA has brought forward is bringing that edge ecosystem into a cloud native type of environment. So all the advantage of microservices and deploying applications here and there in a way where you don't have to worry about package conflicts and upgrades and something, other people are taking care of that for you and you get to focus on the application. So what I like to show here is there's two main elements. One is the security element, all these edge nodes out there being exposed to cyber attacks. Eve only listens to its controller. So in the ZEDEDA controller, there's also an open source controller. This is a Linux Foundation Edge project. And once that is in place, then all of these application, DevOps and security ops and so forth, they all live in their cloud native environment and they don't care where these edge nodes are deployed. So it's really a great, I think, asset for bringing the cloud and the edge under one umbrella. So that's what this slide is about. It turns your edge nodes into a cloud. The DevOps person doesn't actually know that these things are deployed in windmills and trucks and manufacturing machines. So that open edge computing engine, open API to the controller, simplifies the development, orchestration, security. It supports containers, VMs, unit kernels. There's an open API that sets up a TLS. So it's transport layer security between the EvoS and the Eve controller. And that's like your secure tunnel and nobody else can break in. Even if they had physical access to the box, they don't have all that security secrets. So centralized orchestration, you own the edge, and that allows this whole cloud native ecosystem to enjoy the fruits of our labor to bring it to the edge.
Thank you, Casey. So Yeah, so that hopefully got everybody excited about the EVOS. So in the remaining, whatever, 5-7 minutes, let me do a little bit of a speed reading because I really want to highlight a few things of how we actually built it. And the first thing that I wanted to highlight is that we actually picked Alpine Linux to be the base of it, but not in a sense that most people think, right? We didn't pick it to be the base in its standard Linux distribution sense. We actually picked it to be a set of building blocks. Because at the end of the day, operating systems these days no longer need to be integration hubs. I don't want my operating system to be all things to all people. I just want it to be just enough operating system for the use cases that I have. And my use case is that I want my packages to be glorified tarballs because I'm too lazy to build them myself, and I wanted to get an operating system out of the way, so I definitely don't need it to get opinionated on me, when it comes to systemd versus OpenRC, right? I want it to be updated, which Alpine Linux is religiously, I would even say obsessively updated when it comes to security. I want it to have good taste. I want it to focus on small, and again, it really is amazing how much of a focus it is for Alpine. I want it to be not obsessed by cross-compile, but be easily bootstrappable. By the way, I did an initial RISC-V port of Alpine, and it took me literally a couple of days to just get everything up and running inside of my QEMU without, futzing with any kind of cross-compile, setup. And the way we actually leverage Alpine is we take Alpine packages, again, because we're too lazy, and we really like the way that Alpine community is maintaining everything, especially with the focus on security. And we sort of look at it as Maven Central, kind of a repository of just useful bits, right? We put all of those useful bits inside of the OCI containers, and the entire EVOS is effectively composed out of OCI containers, the same way that a typical Linux distribution would be composed out of packages. But again, we don't look at those OCI containers as just sources of bits, right? Then, because we do some additional level of management of these OCI containers, we can actually look at them as effectively micro applications, or as they're known in the cloud native industry, microservices. So effectively, EVOS inside of itself is composed of microservices, and the insights of those microservices come from, a lot of times, from Alpine Linux. In order to achieve all of that magic, we're leveraging Linuxkit, which is specifically designed to compose a specialized operating system in the way that I just described. And effectively, anything and everything that has to do with execution is done through containers. Again, very cloud native-like approach. Now, people typically tell me, like, well, but doesn't it bloat the system? As you could have seen by the stats I was showing, not really. And if we actually really like, the amount of technology that we can get through containers that we don't maintain ourselves. So very quickly now, almost in 2 minutes, porting to RISC-V. Like I said, I did an initial port of Alpine Linux myself, had, my trusted QEMU, also had, thanks to Kathy, my first, RISC-V SBC, which was BeagleBoard, and unfortunately that one is discontinued now. So all of my focus is on this Nezha SBC that comes from Allwinner, which is actually in a way a better board, I would say. So I do all of my work on that, and if you want to join me, buy that board. It's available on AliExpress. You can get it pretty easily. So this is EVOS booting. That's actually Alpine Linux booting, but it's sort of part of the EVOS bootstrap. And basically, the port to RISC-V was very pleasant, and some of it was just given the choices that we made in picking up things like Alpine and Containerd. It wasn't really that big of a deal. So I guess the only thing that I'm still complaining about a lot is upstream kernel, and all of the SBC developers, and Katie specifically, having worked for Qualcomm, knows the pain of device drivers and developers not really keeping upstream kernel up to date with what they're doing. Still very much a pain. Everything else, was pretty easy. A few packages required work, but they were pretty specific, and that was done, pretty easily. So key takeaways from that effort is, I think it is time to start caring about RISC-V, not really on the server, but kind of on the server, but the server that is basically edge, right? And RISC-V versus ARM will be an interesting battle to watch. On the edge, my money is on RISC-V in 2 to 5 years. I'm really excited about how we can change the ISA. And again, all of the virtualization extensions that we're trying to help with sort of fall into that category. And the only question that I have is, if you start with a specialized operating system like EVOS, super easy to get it going, But then the question becomes, what package would you bring to RISC-V? Just wrap it in a container, and we can run it on top of EVOS. Back to you, Casey.
Okay, well, I just wanted to mention that one of the reasons Roman and I are not actually in San Francisco for this RISC-V Design Summit, or RISC-V Summit, is we have an EVE Design Summit going on in 2 days. So you can hop on an airplane from San Francisco. You can probably get to Berlin in 2 days, and you can join us over there. If you can't make that, well, then look on the left side. There's the LF Edge, a whole bunch of links to our meetings, which are bi-weekly, every other week. We have a mailing list. We have a Slack channel. All the source code is on GitHub, and you can build really easily EVOS just by running one Docker command. And one more point, though, is there's a link on that last page to a developer program that I manage at ZEDEDA. So if you want to leverage a commercial EVE controller with your open source EVOS at the edge, just check out that link at welcome-developer, and you'll get set up. So thank you all from Berlin.
Thank you. Thank you for having us. And thank you, Katie. See you all. Bye-bye.
Next time. Are we live?
Hello.
Hey.
Hey, everyone. So do we have any questions?
There were a couple. Did you see the most challenging?
Sure, we can go one by one, I guess. So the first one is, what is the most challenging aspect of RISC-V hardware support with EVOS? So I guess I can take this one. So I would say it was, actually getting access to the hardware itself. So I mean, Sci-Fi RISC-V boards are great, but they're super expensive and not really something that is actually super useful, for the type of sort of operating system that EVE is. So EVE is really meant, for more of a edge, hardware, as I explained. So thanks to Katie, I actually got my hands on one of the first, SBC single board computers, which was actually much more of a, the right fit for the EVOS. Sadly, that got discontinued. So I actually had to move on to the second generation SBC, which is this Neja SBC from, based on the all-winner chip. So that was pretty challenging. The rest was actually pretty easy. I would say that, the upstream on even the basic components like grub and, U-boot is still not what it needs to be, for the kind of SBCs. And the perpetual issue of the kernel support, the drivers are basically always a problem, as, I'm sure
Yep.
Katie knows based on her experience at Qualcomm.
And then, I mean, I totally agree, just getting core upstream driver support was a huge lift for the that early SBC, that beta SBC, and making all of that work was a huge amount of work. We had all sorts of volunteers helping with that and got it to the point of being stable, but then there was a situation with getting access to chips and so forth. The other question about, what is your dream RISC-V board like? My dream is simplicity and affordability with the target of education. I think that a really big advantage, like I say, of getting openness of the silicon all the way through the board and the software, if we can make, the equivalent of the popularity of microcontrollers or Raspberry Pis, it's just something that is a board that's going to be super stable, repeatable. Don't like make it better every 3 to 6 months. Just make it super stable so you can create educational materials around it. That for me would be a huge win. How about you, Roman?
Yeah, I basically, honestly, I just want somebody like a Raspberry Pi Foundation to emerge, so that what you just described becomes somebody's day job, right? I don't think we still have that in RISC-V community. It's great. I mean, all of the innovation that I see coming out of China is simply awesome. But I think, that focus on education and ease of access and just like ease of use, in a way, but sort of turning it into an alternative to Raspberry Pi, like for real, not just kind of like a knockoff of Raspberry Pi, but actually sort of competing with Raspberry Pi. that would be my dream board.
Little birdies have, I've heard little voices in my ear about maybe around embedded world timeframe, maybe there might be some announcements next year for something that suits my dream board.
Awesome. So I guess with that, I mean, there are no further questions. So what I would like to say is like, thank you everyone who actually tuned in to listen to us. Katie, any final thoughts?
I'm just ready for a good night's sleep here in Berlin. It's late.
Me too.
Thank you all in San Francisco.
See you all. Bye-bye.
Bye.